Okay. My name is Jan Soika. I'm the SPA, which is Space, Physics and Aeronomy President. And it's my great pleasure this afternoon to introduce to you our Van Allen Lecturer. This year we honor Bengt Ulf Austin Sonnerup as the Van Allen Lecturer. I'm going to say a few introductory words and then introduce Bengt. It's with great respect I introduce him to you as a senior statesman in our community. I'll explain that in a minute or two. He was born in Malmö in Sweden, and 22 years later he graduated in mechanical engineering at the Chalmers Institute of Technology in Sweden. Before his graduate studies, Bengt worked in the Swedish industry and the military. His projects included gas and steam turbines, which don't relate very well to us. However, the other one was a project on solid propellant rockets. And hence, I will tell you that we can call him a rocket scientist, an honor many of us claim, but have no connection to. Professor Sonnerup completed his MS and PhD in aeronautical engineering at Cornell University. His postdoctoral studies included mentors who are extremely well known by us all, Professor Gold at Cornell and Professor Alfvén at the Royal Institute of Technology in Sweden. Since 1964, Bengt has been a faculty member at Thayer School of Engineering at Dartmouth College. The breadth of Professor Sonnerup's science can be seen by me contrasting only two of his early papers, and these were two papers that he completed prior to 1970. The first one is entitled Magnetopause Structure and Attitude from Explorer 12 Observations. Way back then, Explorer 12 was one of the early ones, and here he is already doing magnetopause structures. However, the other paper I referred to at this point in his career, Magnetic Field Reconnection in Highly Conducting Incompressible Fluids. The contrast there from one to the other is fairly awesome, and both of them pertain to his topic today. I guess the remark I want to make is that he probably wrote the book on the subject that we're about to hear from today. Professor Sonnerup holds the Sidney E. Junkins Professorship at Dartmouth College. He became an AGU Fellow in 1989 and was awarded an Alexander von Humboldt Prize in 2001. His research has focused heavily on magnetospheric plasma physics and MHD. He has over 160 publications, and his co-author lists are a who's who of our field, SPA. He did point out to me in some of his recreational activities. He loves, I believe, walking and hiking, cross-country skiing, swimming and canoeing. The one that struck me as rather interesting is carpentry. And he points out it's not just furniture he builds, it's houses as well. I didn't realize professors on the East Coast get so poorly paid that they have to build their own houses. So, without any more ado, I would like to introduce our speaker, Bengt Ulf Austin Sonnerup. To you as a Viking who made it to America and has flourished.
Can you hear me? Can you understand me? If not, take a crash course in Swedish, will you? Thank you, Jan, for the introduction, the kind introduction. My topic today, as you can see, is plasma and field boundaries in space, and I want to narrow it down a little bit by saying viewing their local structure. And that gives some restriction on the topic and tells you where I'm heading. I list also my co-workers in recent years, and actually they ought to be co-authors of the paper because they have contributed so much information to what I'm going to say. And without them, I would have actually only one more slide, namely this one. This is highly relevant to our field. This is what we do. We look at wiggly curves representing time series of measured information, and we try to make sense out of it. And today I've sat in on a number of talks where people have shown extreme skill in doing that. However, I'm going to do something a little different with the wiggly curve. I'm going to try to transform them into images, pictures. Okay. So first, let me talk about space a little more generally. There are regions in space that contain magnetic field of different origin, and they are separated by relatively sharp boundary layers in the form of electrical currents. For example, if you look on the right-hand picture here, you can see that the terrestrial magnetic field is separated from the external field, which is of solar origin, by the magnetopause current layer. The separation is, however, not complete because of the reconnection process. And I've listened for a full day of reconnection work today. But because of that, there may be a magnetic connection across the magnetopause and an associated transfer of plasma in one direction or the other. In my talk, I will visit the magnetopause in three places. First, in mid-morning at low latitude, and maybe I should try to point at least here. I will be over here and look at the magnetopause that behaves reasonably well. Then I will move on to cusp latitude up here, a little bit on the afternoon side, and we look at the results of reconnection. And finally, I will move to the backside of the picture at pre-dawn magnetopause at mid-latitude and show you an example where we think we saw reconnection setting in. Then I will make a short visit to the so-called low-latitude boundary layer, which is a layer of plasma inside the magnetopause with a substantial flow shear across it, so one might expect to see some signatures of Kelvin-Helmholtz instability there. It's a wide field, and I just have actually one slide to show there. And then I'm going out into the solar wind, not to see all of the discontinuities there, but simply to look at what we call directional discontinuities. Now, here's a picture from Joe Borowski's recent work, and it shows a tangle of flux tubes originating on the sun in the granulation and the supergranulation and reaching a size of maybe 80 to 90 Earth radii at 1 AU. That is, they are much bigger than the magnetosphere. Now, these are, of course, not sitting still in space. You know, I say with Bob Dylan, they are blowing in the wind. And so a spacecraft that sits out here will encounter first, say, the purple flux tube, and then the yellow one that underlies it, and the magnetic field changes direction like this when that happens, and that's what we are going to look at. If you look at the cross-section of this, you get this sort of mosaic picture, all according to Joe Borowski, and you can see that you have very many different orientations, possible orientations of these interfaces or current layers. So, I'll start talking now about the magnetopause, and I want to remind you that the magnetopause was predicted already in the 1930s by Chapman and Ferraro. But it was only really with the magnetometer experiment on board Explorer 12 that Larry Cahill was able to show overwhelming experimental evidence that it was actually there. And in the plot, you can see the measured magnetic field intensity versus radius. And the dipole field is drawn in to help guide your eye. And what you see here is that the magnetic field measured always exceeds the dipole field, and increasingly so as you go outwards, until you get to a point where the magnetopause occurs. In the magnetopause, the magnetic field drops to a quite low level and then recovers and to a lower average level, but with a lot of wiggles. Similarly, the magnetic field directions indicated by the two angles here change abruptly at the magnetopause and then are more non-steady. Okay. The fact that the magnetic field here, right before the magnetopause, is about twice the field of the dipole must have pleased Sidney Chapman greatly, because he had this model of a flat magnetopause made up of the Earth's dipole and an image dipole, and halfway in between there's a plane, and at the subsolar point the field is exactly twice. Okay. So he must have been happy. For my own part, it was really this diagram, this very diagram, together with Larry Cahill's generosity with his data, which was an unusual talent in those days, but he was extremely generous and helped me along, and so I got involved in data interpretation. Okay, so the first thing you can say, what do we do now? Here we have measurements in the magnetopause, and what you can say is we have to have a model. So we say, assume we have a one-dimensional, locally one-dimensional layer, then we would like to find out how that layer is oriented. We would like to find its normal vector. We would like to find its normal field component and the normal velocity, because the magnetopause does not sit still. It moves at tens of kilometers per second in and out. And finally, perhaps the plasma flow-through velocity to see if there's transfer of plasma from one side to the other. Okay. To do this, we need 3 data analysis tools. There are many more, but we only need 3. And the first is minimum variance analysis of the magnetic field. And that involves, as I think most of you know, looking in different directions in space, projecting the measured magnetic field along that direction, and looking for extreme variances in that component. That leads to the variance matrix that you can see up there. The angle brackets is averages over the data set that you have used. And it's a symmetric matrix, so you get real eigenvalues, lambda 1, lambda 2, and lambda 3. And lambda 1 is the largest variance, and lambda 3 is the smallest variance. And then there's a set of corresponding orthogonal eigenvectors, x1, x2, and x3. And those, you will see, are very useful as natural coordinates to look at the data. And then the next step is to predict the normal direction as the eigenvector of the smallest variance. Now this looks like you're on solid grounds here. If you believe in Maxwell's equations, divergence of B is 0, and in one dimension that means that the normal component of the magnetic field doesn't change with space. If you believe in Faraday's law in addition, you can conclude that it also does not depend on time. So you think you are on firm ground, but there is a proviso. There must be a good separation between the intermediate and the smallest eigenvalue. And as long as you have that, you are hopeful that you have gotten a good normal, which is not always true. So you use the ratio of those two eigenvalues as a quality measure, and at the magnetopause one has typically thought you need a ratio greater than 10 in order to get an accurate normal. Oh, sorry. You missed all of that. But no loss, you already knew it. Okay, so I will try to keep my mouth close to this. Now, once you have done this, you can calculate the average normal component. Second method is called the Hofmann-Teller analysis. It is finding a moving frame of reference in which the electric field is as small as possible. In my work today, I will use only the convection electric field, and the way to find the velocity of the frame is to minimize the electric field in the moving frame. Okay. Now, once you have done that, you can dot it into the normal, which you got up here, and you can therefore find out how fast the magnetopause is moving, and you can calculate the flow-through velocity as well. Now, the Hofmann-Teller analysis actually can work for 2- and 3-dimensional structures as well, provided there is a natural, a proper frame in which the electric field is reasonably small. Third method is called the constant velocity approach. It's a force-spacecraft timing method that gives you both the normal and the velocity of the structure along the normal. This was first used by Tom Axon and his co-workers with IC data to find the Hofmann-Teller frame velocity. But they did it by trial and error, however. The last method was first used, I believe, by Chris Russell and his co-workers in 1983. So, let us take a quick look at what the first 2 methods can give you. Here, over on the left, you have the Wiggly Curbs that I've been talking about, representing the free magnetic field component. And you can see that the Z component, Z component, is pointing up. That indicates you may be in the magnetosphere, and then it moves down and you have moved into the magnetosheath. And the density profile confirms that you start at the low density in the sphere and wind up at the higher density in the magnetosheath. Okay. Now, let us do minimum variance analysis on a time segment in here that is optimal in some sense. And we represent the data in terms of magnetic hodograms. And along the vertical axis in the left hodogram, you put the component of the magnetic field along the maximum variance direction. And on this axis, the horizontal axis, along the intermediate variance direction. And in the same way, in a different projection, maximum variance component vertically and minimum horizontally. And it's now that you see that this method has given you something. And what it's given you is that the component of the magnetic field along the minimum variance direction is small. And not only that, the fluctuations are fairly small compared to the fluctuations in the intermediate component. And in fact, the eigenvalue ratio that you can see down on the first line below is 19.5, and that's certainly satisfying. The normal vector itself is also what you expect, given that this is in the morning side, mid-morning, and near the equator. It points outward from Earth and has the negative y component that you expect and the near zero z component. The normal field component is 0 within statistical errors. Okay, so that's that. Now, to do the Hofmann-Teller determination, of course, you need measurements of velocity as well as magnetic field, and I assume I haven't shown those plots, those wiggly curves, but the result is a velocity that heads over to the morning side and tailward, and with some component in the northward direction as well. It's basically tangent to the magnetopause, but not quite. It's got a small negative normal component, which indicates that the magnetopause is moving towards Earth, inwards. And that's exactly what it takes in order to make a transition from the magnetosphere to the magnetosheath. So it all works out pretty well. This number is pretty uncertain because it's hard to determine. But accuracy of the de-Hoffmann-Teller determination you can view by plotting the three components of V cross B against the corresponding components of VHT cross B. And if you have a perfect de-Hoffmann-Teller velocity, the points line up along the 45-degree line. Now, it's doing pretty well here. And I want to make the comment there that if all your points had been in a clump down there, you shouldn't necessarily believe that you have a good frame of reference. But this is a good de Hoffmann-Teller frame. And we can now go on to the last part of this slide, which is the so-called Wallén test. Now, Claes Wallén was a Swedish solar physicist who in 1944 published the first analysis of large amplitude Alfvén waves. And so that's why this is called after him. It's meant to test whether you have such a structure, which we now tend to call a rotational discontinuity. And what is plotted in this scatter diagram is the velocity in the de Hoffmann-Teller frame, component by component plotted against the corresponding components of the measured Alfvén speed. And if you have a good RD, then all the lines are either on the positive diagonal or along the negative diagonal, depending on whether the flow is along the magnetic field or opposite to the magnetic field. You can see that neither is the case here. In fact, the velocities are fairly small in the de Hoffmann-Teller frame. So our magnetopause flunks the test. It's not a rotational discontinuity. It also has no significant normal component, which is consistent with that conclusion. But it must be then what we call a tangential discontinuity. And so what do we do next? Well, this is the end of the line as far as one-dimensional analysis goes. You now need to go to 2 dimensions. And you can note that actually in 1 dimension, the normal component shouldn't have any fluctuations at all, but it does. Okay. So we would think that try to explain that in terms of 2 dimensions now. And since the velocity in the de Hoffmann-Teller frame is small, we can think that if we move in that frame, we have a steady structure which is magnetohydrostatic. And if it's 2-dimensional, it's governed by the Grad-Shafranov equation. And you can use the Grad-Shafranov equation to produce a map of the magnetic field in a direction perpendicular to the invariant direction, which is out of the screen. Okay, and you see the resulting field lines here. The color code describes the axial component of the magnetic field, and you can see that there is some current filamentation leading to magnetic islands, or rather to flux ropes. Maybe these are sort of baby FTEs, but there is no other indication of reconnection in this situation. So how was this produced? First of all, the spacecraft trajectory. This is all based on data from one spacecraft. And the spacecraft trajectory is along the x-axis, and we've converted time to space information by using the x component of the de Hoffmann-Teller velocity, and we have plotted as white arrows the measurements of the magnetic field projected onto this reconstruction plane. The orientation of this plane, in this case, happens to be sort of approximately in the meridional plane in mid-morning, okay? And this end points to the north. So the spacecraft looks like it's traveling through in this direction from left to right at high speed, but in reality, it is the structures that are moving from right to left at high speed northward, right? Okay. The normal vector that we calculated before sits here, and it looks pretty good. Now, I don't want to get hung up on equations, but you should see the Grad-Shafranov equation at least. It describes the behavior of the one-dimensional vector potential, which is in effect a stream function for the field lines, so that A constant describes the field lines. Now, BC The axial field is a function of A, and P is a function of A. And we can obtain A on the x-axis simply by integrating By, because By is minus dA dx. So that looks like we can get A on the x-axis. And since we know P and BC square on the x-axis, we can get those as functions of A. And once we have that, we know the right-hand side of the Graf-Shafranov equation. This term we also know because we can do x derivatives along the x-axis, right? And so we can calculate the second derivative here. And then we stick that into a Taylor expansion, and we step forward in y, one step at a time. The procedure is, strictly speaking, illegal because it is an ill-posed mathematical problem, and it may be a felony in mathematics circles. But it's clear that one should do this kind of thing because surely you don't know, if you measure along a line here, that's not the only thing you know. You know things a little bit away from that axis as well. And we are using the equation in order to inform us about that. The numerical instability consists of rapidly growing spurious solutions that you pick up. And to try to suppress those, you have some low-pass filtering in each step of the integration. And you can still ask, still you get a fairly narrow height of your window. But you can ask if this really works. And so the next slide here shows a benchmark test. We have a particular form of the Graf-Shafranov equation. We have an exact solution of it, and we measure data along the x-axis of that exact solution, which is on top. And then we do the reconstruction, and you see that we get something that looks pretty good. So let us move on now to talk about flux transfer events. We are now on to the cluster period. And this flux transfer events were actually first identified and studied by Chris Owen. What you have now, since you have 4 spacecraft, is many more wiggly curves to deal with. But for the plasma information, you actually only have 2 because the plasma instrument was fully functional only on 2 of the 4 spacecraft, namely cluster 1 and cluster 3. And you can see that cluster 1, if you follow the trace, the black trace up in the top panel, it starts out with low density in the magnetosphere. There's a substantial boundary layer, and then you get across the magnetopause, where you can see below that the magnetic field is changing, and then you stay in the magnetosheath. Whereas cluster 3, which was closer to the Earth, stays in the magnetosphere, except for some brief excursions that may have been encounters with the boundary layer, I should say. Okay, and so in fact, all of the spacecraft, except spacecraft 3, goes outside, and only spacecraft 3 stays inside the magnetosphere. Look now at the field magnitude, which has 3 big pulses here. And those are the signatures of the 3 flux transfer events. The normal component is way down at the bottom, and you can see the bipolar signature that led Chris Russell and Rick Elphick to take an interest in this and to imagine that they were flux ropes embedded in or lying on the magnetopause. Turns out they had a pretty good guess. So now we will take those 3 and take all the data from the 4 spacecraft and convert into a map. 3 maps, 1 for each FTE. Now, it's actually that each of these maps is made up of 4 maps. 1 map made from each spacecraft, and then they were weighted appropriately and shifted in X and Y so that they should overlap, and then you overlap them and produce the composite, a composite map. That's what Hiroshi Hasegawa did. And the composite map, of course, no longer satisfies the Graf-Shafranov equation, but it has the plus that it has a quite good predictive capability. Here I have predicted field components versus measured field components, and you can see that we get good correlation coefficients. Go on, one more slide here. If we look at FTE2, we see that it is quite a big structure now. This is a full-grown, no longer a baby, it's a full-grown structure, and it has a very strong core field. So it is a flux rope embedded in the magnetopause. I don't see how this strong core field could really come about except if the reconnection process that generated it was component reconnection, that is, reconnection of field lines that formed a finite angle rather than being anti-parallel. If you go to the bottom panel here, that has plasma pressure in it instead. And you see the higher pressure in the magnetosheath and the lower in the sphere. And in the FTE structure itself, the plasma pressure first goes up and then drops to a low level near the center. This seems to me to be an indication that at least the center is connected to the magnetosphere somehow. And if it is, then there should be an ionospheric footprint, perhaps in the form of a poleward moving auroral form or PMAF. But it's not so easy to tell exactly where it is, and it certainly has not been identified. If you look at the velocities that are left over, and those are those little white arrows here, you can see that there is some velocity in the spacecraft 1 measurements that indicate that this tongue sticking out here is the field lines are actually moving to the left. So the picture is not time independent, it is time aliased to some extent. If you look down in the magnetosphere, you see these enormous velocity vectors here. And that's because you're traveling to the left with high speed on board these FTEs. And the result is that, the plasma here looks like it's moving backwards. It's like being on a bullet train and seeing the houses sweeping by in the opposite direction. The flow, in fact, is more or less field aligned, and it's also supersonic. And this is of interest to fluid mechanicists because it is basically flow in magnetic channels that are converging as the magnetic field drapes over here and then diverging again. And of course in subsonic flow, the result of that is that the flow speed goes up when it goes under the hump and then slows down again. In supersonic flow, it's the other way. The flow slows down in the middle here where the cross-section of flux tube is as small as possible and the pressure goes up. In fact, the measurements show that, but because there's a boundary layer draped around here, and you penetrate into that, you can't really tell for sure. So now I haven't said anything about how you find the invariant axis, but that's a very important item when you do these reconstructions. This is a view of a unit hemisphere, or rather just 12 degrees of it from top. In the equatorial plane lies the normal vector that we got from minimum variance analysis of the magnetopause crossing that came a little before the FTEs, and the various points here are different directions on the invariant axis from 4 different methods. Note that all the measurements are actually pretty close to this line, and on this line you are exactly perpendicular to the normal. Okay. So within errors, all 4 methods gives you something that is perpendicular to the normal vector, and therefore that's what you need if it's embedded in the magnetopause. So we now go on and look at the individual methods. What Hiroshi Hasegawa did here was to look at, try different directions, do reconstructions, get those correlation coefficients 2 slides ago, and try to maximize them. And the result is this point here called GS. That's a multi-spacecraft technique. The second method is different. There you go into the de Hoffmann-Teller frame, thinking that's the right frame to be in, And then you look at the leftover electric field. And if you believe that it's a time-independent two-dimensional structure, then Faraday's law tells you that the Z components, the component along that invariant direction, should be constant. And in fact, that invites you to do minimum variance analysis on that electric field instead. And indeed, you find that the variance is some 10 times smaller in the direction that we select, and it's shown over here. Okay. But then you can go on and say, well, maybe the de Hoffmann-Teller velocity isn't quite the right frame, because after all, the electric field is not zero as it should be. So you can go ahead and do an optimization both with respect to the z-axis orientation and the frame velocity, and then you get to this point called nu. Finally, then, this is the oldest method. If you travel through a flux rope, you encounter each field line twice, or each A value twice. And since BZ is a function of A, BZ should have the same value at the two places. And if it doesn't, maybe you don't have the right invariant axis. And so that method led to this point over here. Now, the fact that these all fall pretty close together, and that they are all essentially perpendicular to the normal direction, convinces me that it's not nonsense to talk about an elongated structure that has an invariant axis. Exactly how long it is, we can't tell right now. So on to the business of magnetic field reconnection at the magnetopause and the onset of it. We are now over on the pre-dawn side at mid-latitude, and this is a map produced entirely by data from cluster 1, and cluster 1 therefore sits at y equal to 0, sits on the x-axis. And what you see is another one of these quiescent tangential discontinuity structures with some swellings here and there, but a tangential discontinuity. And the Valence slope is as high as 0.57, but it's actually dominated by measurements here and here, so all it's saying is that the flow outside of the structure is 57% of the Alfvén speed. It doesn't indicate that there's any reconnection going on, and there's no sign of reconnection. The map, of course, predicts that spacecraft 3, which crosses some 30 seconds later, should see the same thing. But that ain't so. Instead, you see reconnection in full swing. Now, these maps here are based on a different reconstruction technique. Instead of Grad-Shafranov, we are now integrating the full MHD equations, and it can be done. And the advantage of that in terms of reconnection is that you can now put yourself in the frame of reference of the X-line, which is not the same frame as if you try to do the Hoffmann-Teller analysis. And you see that indeed there is an X in the map here, and there's a big wedge of reconnected flux field lines, I should say. The thing that is interesting about this is also that the difference in color between here and here. It indicates that the guide field, BZ, is not constant. This was very disappointing to me, and I fought it for a long time, but the result didn't change. And what we found instead is that what our optimal axis is only 6 degrees off the prediction by Swistak and Drake, which is based on choosing an axis orientation, choosing an X-line orientation such that you maximize the flow velocity in the exhaust jet from reconnection. And since the invariant axis in this kind of thing must coincide with the X-line, then this looks pretty good. The second panel, because we do MHD, we now get streamlines as well. And the second panel shows the streamlines in black. And you can see in the color that actually the axial component of the velocity has a big shift in it too, as you expect when you have a big shift in the guide field. The bottom panel shows an overlay of field lines, black, and streamlines, white. And you can see that there's flow into this this wedge of reconnected flux from both sides, both from the magnetosphere and from the magnetosheaths. The color that you see down here is an indication that the velocity is high. And this is, in fact, the plasma jetting that was first seen by IC in 1979. The valence slope is 1. And that's what you expect from the model that Levy, Pecek, and Cisco produced in the early 60s, which is dominated by a rotational discontinuity. And so that looks good as well. And the reconnection rate, or at least the lower bound on the average reconnection rate, you can estimate from the amount of flux contained here, the reconnected flux, and it must have been created in 30 seconds or less. Now, let's make a quick visit to the low latitude boundary layer. Since we now know how to do MHD reconstruction, we can reconstruct streamlines in the low latitude boundary layer. It's a slightly low latitude and slightly over in the afternoon. And what you see is 2 vortices. There are in fact more of them, and if you could extend the integration well, if you could use a longer X value, use more data simply, you'd see more of them. But they are undoubtedly created by the Kelvin-Helmholtz instability, and they may not be entirely properly represented in this kind of simple reconstruction. But the magnetic field is mostly out of the screen here, but there are some small components in the plane of the screen, and those are wrapped up into a magnetic island here. So here you actually have a flux rope, and there's another one over there. Those features ought to project into the ionosphere with an appropriate transfer function and should be visible in the high latitude ionosphere. Now the bottom panel shows an overlay of field lines, which are black, and streamlines, which are red. And you can see that they are not the same. The flow is not exactly along the magnetic field. They are similar, but not the same. And what that means is that this map is not time independent. It's time aliased, and the flow must be deforming the island and rotating it and so on, if you look at it in detail. Okay. Now the final topic, directional discontinuities in the solar wind. Are they tangential discontinuities or rotational ones? I'm focusing only on the normal component of the magnetic field, but there are other differences that can be taken into account. At any rate, early spacecraft studies using MVAB gave a 50-50, roughly speaking, mix of rotational and tangential discontinuities. Using cluster, Torsten Knetter tried to recover this result, and he did when he used MVAB. But when he used this timing method instead, he found that none of his 366 cases in his thesis were confirmed rotational discontinuities. It doesn't mean that they couldn't have been. It only means that the normal component was so small that it was within the errors of the timing method, and those errors are not negligible. But he also found that on the average, the agreement with MVAB normal vectors and CVA ones becomes better the larger the eigenvalue ratio. So this confirms that this is a useful parameter. But even for very large values, you can get totally the wrong prediction. And I want to demonstrate that to you. Oh, see. Oh, yeah. Oh, yeah. Okay. Let me... This is an MHD reconstruction of a solar wind discontinuity. This is difficult to do because they blow by pretty fast and you don't get much plasma data. But here is one, and you can see the map to the top over here, and you can the discontinuity is more or less oriented this way, but it's got a big island in it. And as a result of the big island, you see the following. If you do the timing method, you get a pretty good normal. It points sort of where it ought to be pointing. It's the gray vector over here in the map. If you do minimum variance and constrain it to say the magnetic field on average normal magnetic field on average must be 0, then you get this cyan color. This also not so bad. But if you do minimum variance analysis, the yellow arrow, without any constraints whatsoever, you get that tiny little yellow arrow there. And it's tiny because most of it points along the axial direction, points out to the plane. So how can we, what's happened here is that the minimum variance method, if you make the identification that the normal is x3, goes completely wrong. Because the normal ought to be pointing more or less along the x-axis. And why is that? Well, look at the 3 panels below the map, and what you can see there is the black curves representing the actual measurements on cluster 2, 3, and 4. And if you look at those alone at first, you can see that the BZ component, and these are now reconstruction axes, so this is the axial field. It changes a little bit. It has a ramp in it, and it's reflected in the color up there, but it's not changing an awful lot. On the other hand, the X component has big variations in it, and that's the result of the direct result of the magnetic island. Okay, so the magnetic island really wrecks your life at this point. So that is the explanation. The minimum variance method is certainly going to say that this is the minimum variance direction. So what is this? Is it a tangential discontinuity? Is it a rotational discontinuity? We don't get enough of a field of view to really tell for sure, but there are some clues. If you take and do this Valence test now, you find the result on the bottom right here. And that shows you that the data are beautifully lined up on the positive diagonal, and they are well spread out as well. This is a good satisfaction of the Valence test. So that is consistent with the rotational discontinuity. The slope is positive, so the flow is along the magnetic field like this. Another item is that the magnetic field magnitude is also nearly constant, and that's another property of rotational discontinuities. Finally, you have this question, what's going on with the prediction versus the measured values? The agreement is not overwhelming. It is, roughly speaking, right. The map does a decent job, but not a very good job. And why is that? Well, we argue that this is because of time evolution of these structures. And I will show you that in the next slide in a moment, but let me say how that slide is obtained. It's not this discontinuity here. It's another one, and it's a Grad-Shafranov reconstruction. And then you look at the leftover velocities in the de Hoffmann-Teller frame and realize that they deform the structure, and you kinematically describe what that time evolution is. And that is what you see on the next slide. And what this is the duration of this movie is actually shorter than the time it takes the spacecraft to move from one side to the other. Okay, and what it tells you is that in this case you have some pretty severe time aliasing problems, and that we think is the explanation for the less than perfect agreement of the stationary map. Okay, I'm going on to one more example of discontinuities in the solar wind, and this is an entirely different type, and one that we cannot reconstruct, in fact. But the hodograms are extremely interesting because look here over on the left. This is a cluster observation, cluster 1 in fact. It shows the magnetic field, tangential magnetic field, swinging up rapidly up to here and then turning around and going back with a lot of hesitation and a lot of wiggles, and a lot of wiggles also in the normal field. So it looks here like the normal field component is small but slightly negative. The eigenvalue ratio is not convincing, however. So if we do the analysis on only the inner branch of this peculiar hodogram, then we find an eigenvalue ratio of 230. That's the highest value I have ever seen. And we have tested this, and the normal component is positive, and it's a robust result. It's not big, but it is robust. So it is positive. And if we now look at this flow-through velocity that we haven't talked about before, you find that that's also positive. Of course, both of those results are very sensitive to the normal. But the fact that they have the same sign is consistent with the overall Valence slope, which is positive, and that, of course, the Valence slope has nothing to do with the normal. So it looks like we have got the right signs on this. Finally, the thickness of this, it's blowing by pretty fast. So it's 20 ion inertial lengths thick. Here's another example from the work of Bruce Tsurutani. It is basically the same. It's a little messier, so it's hard to see the separation of the inner and the outer branch of the hodogram. But there is an important difference. In this case, the outer branch, the slow, wiggly branch, comes first, and then the return is rapid along the inner branch. And the normal component, calculated again from the rapid rotation only, is firmly negative and has a good eigenvalue ratio, so it's a believable result. So a negative normal magnetic field component, the flow-through velocity is positive, as based on only 4 data points, because the time resolution was not terribly good for the plasma information. But the fact that it's a minus here and a plus there is consistent with the negative Valence slope. So there is, in fact, a family of exact ideal solutions, wave train solutions, where the hodograms look like what we see. If you have Vn prime and Bn the same sign as you do for cluster, then you move up along the inner branch and move back down again along the outer branch. If you have Vn prime over Bn negative, then you reverse the arrows and you start out going on the outer branch and go back along the inner branch. The inner branch in the model is ion polarized and has Alve number slightly less than 1, and the outer branch is electron polarized and has Alve number slightly greater than 1, and right at the turning points here, the Alve number based on the normal components is exactly 1. Now that allows you to interpret what's going on. The outer branch is an electron whistler, and it can stand in the flow only if the Alve number is slightly greater than 1, because its phase velocity is slightly greater than the Alve speed. And the other one is the ion branch, and it has to have Alve number slightly less than 1. So one understands why how this behavior comes about. The thickness scales as the ion inertial length divided by an squared minus 1. So having an squared close to 1 allows you to get quite large thicknesses out of the model. Now, there is, however, a fly in the ointment, a big fly in the ointment, and that is that the branches have the same duration in the model, whereas in reality you see that one of them is slow and has a lot of wiggles in it, and the other one is fast. And the reason for that we don't understand exactly right now. There are other peculiar things. The normal vectors from all 4 spacecraft obtained from variance analysis is extremely well determined, and it's quite different for the 4 spacecraft. Here's spacecraft 4, here's spacecraft 3, that follows in time, then spacecraft 2, which is, I'm sorry, this is 4, and this is 2, and this is 3. Those 2 are only separated by 1 second, and finally there's spacecraft 1. And the timing normal sits over here. Now, this kind of thing indicates that there is actually must be spatial structure as well as temporal structure on the spatial scale being the spacecraft separation, half an Earth radius or so. There's another thing, and that is that C1 and C3 sees earthward propagation of the normal, whereas C2 and C4 sees sunward propagation. And that again indicates there must be some really peculiar structure here. Finally, to conclude this, we found that discontinuities often contain significant quasi-2D structures, flux rope, X-lines, etc. And presumably there are strong three-dimensional structures as well, so that at the moment we don't know how to describe. Now, the structures can do serious damage to minimum variance determinations of the normal. That much is clear. A large eigenvalue ratio helps, but not always. You have to be careful. I would say if you get a good eigenvalue ratio, but the normal component, or a solar wind discontinuity, is big, then probably you have the wrong normal. You should have chosen the intermediate variance direction as the normal, and you would have done better. The structures, as I've discussed will make it hard to distinguish between TDs and RDs from the maps, at least. And finally, let me say that you can do 2D reconstructions, not only in Grad-Shafranov and in ideal and resistive MHD, but in Hall MHD and in two-fluid. They're all doable, but they're all aliased by time variations, I think, to some extent or another. And they all are also aliased by Z variations, because the spacecraft flies through with a component of the Hoffman-Teller velocity along the Z-axis as well. Still, it looks to me like they can be useful tools for understanding field and flow structures, including reconnection. Now, the next challenge is really to recover 3D features and time dependence. And Hiroshi Hasegawa and I are starting to work on those problems and have done something already about the time dependence, which you could see in the movie. So, to close this, here is Professor Van Allen in 2004 at age 90. You will note that he is in his office, which should serve as a spur to all of us, but in particular to us older folks. Thank you very much.
On behalf of the SBA organization, I wish to give Professor Sonnerup a memento of this talk he just gave us all.
I will answer questions.